Hello. In this video for Chapter 5, MAC2233, Calculus for Business Social Sciences, we're looking into second derivative. Now, we just did some second derivative word problems to see that first derivative is like velocity, second derivative is acceleration. The second derivative is how the first derivative is changing. Well, another application of second derivative is to talk about concavity. Curve is concave up. If its slope is increasing, the second derivative is positive. A curve is concave down. If its slope is decreasing, the second derivative is negative. So concave up is like a happy face. Concave down is like a sad face. So another application of second derivatives, not a major application, but another application of second derivative is you can find out when a graph is concave down or when a graph is concave up by looking at the second derivative. A long time ago, we didn't have graphing calculators. We had to maybe do it by points to see what was going on. So we could find the behavior of concave down or concave up by looking at the second derivative. So an example, if we had the function x cubed minus 3x, which is shown here, is going up, down, and up again, the first derivative would be 3x squared minus 3. And the second derivative would be 6x. So if we pick a point and plug it into the second derivative, if it's a positive number, it's in a concave up. If it's a negative number, it's in a concave down. If the result is 0, we'll talk about it. So if I look at a point like negative 1, and I plug negative 1 into the second derivative, my result would be 6 times negative 1 is negative 6. Now it's a negative 6, which means that it is in a concave down area. If I take a number like, let's say, 2, 6 times 2 is 12, but it's a positive 12, which means that is in a concave up area. Now, if I plug in 0, 6 times 0 is 0. It's a point where it's neither concave down nor concave up. That is called an inflection point. That's where it changes from concave down to concave up or concave up to concave down. So that's kind of an interesting point, is where it changes. So how to find an inflection point? You take the second derivative, set equal to 0, and solve. Find x, plug it into the original to find y. So we're going to skip this example, and we're going to talk about analyzing a graph. Okay? So when we analyze a graph, there's some things we're going to look into. We're going to look into finding the x and y intercepts. Remember, to find an x-intercept is where y is 0. To find a y-intercept is where x is 0. We're going to look at the extrema, which would be the stationary, singular, endpoints, all the things we would talk about in Chapter 5. Points of inflection, which we talked about. You take the second derivative, set it equal to 0, and solve. Behavior near points where the function is not defined. So we're going to look for asymptotes in 4 and 5, vertical and horizontal asymptotes. Okay, so let's look at the example. If we're trying to analyze the graph, the function 1 over x minus 1 over x squared, which looks like this. To the left of 0 on the x-axis, it kind of goes down. And then to the right of the 0 on the x-axis, it goes up, and then kind of falls back down. Okay? So, to find the x-intercepts, we're going to take the graph, the function, and set it equal to 0, where y equals 0. So, if I set y at 0 to find the x-intercept, we get 0 equals 1 over x minus 1 over x squared. To solve, we can make a proportion by adding 1 over x squared to the other side, 1 over x squared. We get 1 over x squared equals 1 over x. Cross multiply to solve proportion. X squared times 1 is x squared. 1 times x is x. Then we're going to move everything to one side, so I subtract x, which leaves us with x squared minus x equals 0. To solve that, we factor out an x, so we have x parenthesis x minus 1 close parenthesis equals 0. Set each one equal to 0, x equals 0 is x equals 0, x minus 1 equal to 0, add 1, x equals 1. So we have two x-intercepts at 0, 0, and 1, 0. But when we look at the graph, 0, 0 isn't there. Something's going on there. It's probably going to be an asymptote. But we do have an x-intercept at 1, 0, so that is true. For a y-intercept, we go to the original function and make x 0. Well, when I plug x into 0, that's undefined. Something's going on there. But the bottom line is there's no y-intercept. But again, it looks like there's an asymptote or something going on there. Okay, so as far as x and y-intercepts, we do have one x-intercept at 1, 0. 1, 0. So to find the extrema, we're going to go through stationary, singular, endpoints. So stationary, we take the first derivative, set it equal to 0. So we can rewrite 1 over x as x to the negative 1, minus, we can rewrite 1 over x squared as x to the negative 2. So the derivative of x to the negative 1 minus x to the negative 2, the derivative of x to the negative 1, bring the negative 1 to the front, subtract 1, we get negative 1 x to the negative 2. Negative 2 times negative 1 is positive 2. Negative 2 minus 1 is negative 3. So the derivative would be negative 1 x to the negative 2 plus 2x to the negative 3 set equal to 0. Now to solve this, could take a little bit of algebra. So first thing I would do is make these negative exponents positive by moving them to the denominator. So I have negative 1 over x squared plus 2 over x to the third. So I would add x squared to both sides. That's plus 1 over x squared plus 1 over x squared. So 2 over x to the third equals 1 over x squared. We have a proportion again. Cross multiply. X to the third times 1 is x to the third. 2 times x squared is 2x squared. Move everything to one side, set equal to 0. So I subtract 2x squared, subtract 2x squared, and we're left with x cubed minus 2x squared equals 0. To solve that, we're going to factor out an x squared. So we get x squared parenthesis x minus 2 close parenthesis equals 0. X squared equals 0, which leaves us with x equals 0, which we know when we plug in 0, we get undefined, so it's not a stationary point. But x minus 2 equals 0, we add 2, we get x equals 2. 2 is a possible stationary point. 2 is a possible stationary point. When I plug 2 into the original, we get 1/4. So 2, 1/4. And if I look at the graph, 2, 1/4, that would be an absolute max. It's to the left lower, to the right lower. That would be an absolute max. So in stationary, we find 2, 1/4 to be an absolute max. Now for singular point, it's where the derivative is undefined. So remember, the derivative is 1 over x squared plus 2 over x to the third. Well, if I plug in 0, it would be undefined. But if you go to the original and plug in 0, again, it would be undefined. Something's going on here, and that's what we'll research soon. So there are no singular points. Endpoints would be the domain. No domain was given, so there's none. So as far as extrema, we found 2, 1/4. That would be an absolute max. For points of inflection, this is the new one. To find points of inflection, we take the second derivative. Well, we've already taken the first derivative, negative 1 x to the negative 2 plus 2x to the negative 3. To find the second derivative, we take the derivative again. So negative 2 times negative 1 is 2. Negative 2 minus 1 is negative 3. Negative 3 times 2 is negative 6. Negative 3 minus 1 is negative 4. So the second derivative would be 2x to the negative 3 minus 6x to the negative 4. Again, to solve this, set equal to 0. But I'm going to make these negative exponents positive by moving them to the denominator. So 2 over x to the third minus 6 over x to the 4 equals 0. We're going to make a proportion. We're going to add 6 over x to the 4 to the other side. So we have 2 over x to the third equals 6 over x to the 4. Cross multiply. 2 times x to the 4 is 2x to the 4. 6 times x to the third equals 6x to the third. Subtract 6x to the third to the other side. So we have 2x to the 4 minus 6x to the third equals 0. We're going to factor out a 2x to the third, parenthesis, leaves me with x minus 3, close parenthesis, equals 0. 2x to the 3 equals 0, therefore x equals 0. X minus 3 equals 0, add 3, x equals 3. We already know that 0 will not work, but if you plug in 3 into the original, you get 2 over 9. And if we go back to the graph, 3, 2 over 9 would be right about here on the graph. Notice where the graph is going down. It's turning from concave down to concave up. Where that happens is 3, 2 over 9. So we do have an inflection point at 3, 2 over 9. Now, for behavior near points where f is undefined, basically we're looking for vertical asymptotes. We're looking for vertical asymptotes. So to find vertical asymptotes, we go to the original, and find out where is it undefined. So at the original, it is undefined if I plug in 0. So the original is undefined at 0, therefore we have a vertical asymptote at 0. That's where the graph cannot cross.